Hello, in today's video, I'll be solving questions on A-level Electrochemistry from October-November 2019, paper 4-1. Question 1. An electrochemical cell is constructed using two half cells, an SN4 plus slash SN2 plus half cell and an Al3 plus slash Al half cell. A. State the material used for the electrode in each half cell. In constructing half cells, when you have two ions in the half cell, in the case of the SN4 plus slash the SN2 plus half cell, it means that the two ions must be in solution in this case. And then you connect a platinum wire to the voltmeter and then dip that inside the solution of the two ions. But if the half cell is made up of an ion and its metal, in the case of the Al3 plus and Al half cell, the ions must be in solution and then the metal must be dipped in the solution of the ions. So which means that this metal is the electrode and then the platinum wire is the electrode in the case of the ion slash ion half cell. So the electrode is platinum for the SN4 plus slash SN2 plus half cell, and aluminium is the electrode for the Al3 plus slash Al half cell. B. The cell is operated at 298 Kelvin. The Al3 plus slash Al half cell has standard concentrations. The SN4 plus slash SN2 plus half cell has SN4 plus concentration as 0.300 mole per decimeter cube and the SN2 plus concentration as 0.150 mole per decimeter cube. I. Use the next equation to calculate the electropotential E of the SN4 plus slash SN2 plus half cell under these conditions. The next equation is used to calculate the electropotential of a non-standard half cell. We can see that the SN4 plus slash SN2 plus half cell is a non-standard half cell as the concentrations are not standard. Standard concentrations will be 1.0 mole per decimeter cube for both ions. As this half cell is not a standard half cell, the electropotential value is calculated as the E naught of cell, the standard electropotential value of this cell plus 0.059 over Z, which is the number of electrons transferred in this half cell, log concentration of oxidized species over the concentration of reduced species. From the data booklet, the half cell equation is given as this, and the electropotential value for this half cell is plus 0.15 volts. The SN4 plus is the oxidized species, and then the SN2 plus is the reduced species. The oxidation state is plus 4, and that has been reduced to plus 2 in this case. So it means our electropotential is equal to 0.15 volts plus 0.059 over the Z is the number of electrons transferred in this equation, which is 2 electrons. So we put 2 there. Log concentration of the oxidized species, and in the question it is 0.3 divided by concentration of reduced species. From the question it is 0.15. This gives us plus 0.16 volts. II. Calculate the electropotential of cell under these conditions. We can only solve for E of cell when we have a complete cell. And so the complete cell is gotten by adding these two half cells together. Once we have that complete cell, we can add the electropotential values together to get the E of cell. The Al3 plus to Al half cell is a standard half cell, so we get the electropotential value from the data booklet. The SN4 plus to SN2 plus half cell is a non-standard half cell, and so we calculated the electropotential value in I above. Looking at these two electropotential values, this one is more positive, which means this is the positive pole and reduction occurs at the positive pole. And so once this equation is written in the reduction form already, it means that you have to maintain this electropotential value. So that will be 0.16 volt plus, once this one is already undergoing reduction, it means this one must be made to undergo oxidation. And so we have to reverse this equation. Once we reverse this equation, the sign of this electropotential value must also be reversed. So it becomes positive. So that will be plus 1.66 volt. And that gives us 1.82 volts. Write an equation for the overall cell reaction that occurs. So we can get the cell reaction by adding these two half cells together. But for you to add the two half cells, you must make sure that the electrons transferred in both equations are equal. To do that, we have to multiply this equation by 2 and also multiply this equation by 3, and that will make the number of electrons in both equations 6. After the multiplication, these are the resulting balanced equations. Now, the electropotential value for this equation is more positive, and so it means that this equation must be undergoing reduction. So we have to maintain this equation. So you have 3SN4 plus 6E minus, giving us 3SN2 plus. Now, since this one has a less positive electropotential value, it means that it must be undergoing oxidation, and so this equation must be reversed in order to write the full cell equation. So this will be 2Al giving us 2Al3 plus 6E minus. So adding these two equations up, we add the reactant side to reactant side and product side to product side. So that will be 3SN4 plus 2Al plus 6A minus, giving us 3SN2 plus 2Al3 plus 6A minus. The number of electrons on product side is the same as number of electrons on reactant side. So we cancel the two together. And our resulting equation is 3SN4 plus 2Al, giving us 3SN2 plus 2Al3 plus. And if you check, all the atoms and charges are balanced. C. Aluminium is produced industrially by electrolysis of a melt containing large amounts of Al3 plus ions. Calculate the mass of aluminium that is obtained when a current of 300,000 amps is passed for 24 hours. Give your answer to 3 significant figures. Now, the first thing I want us to do is to convert our time to seconds, because we use time in seconds. And so for 24 hours in seconds, you know that 1 hour is equal to 60 minutes, and 60 minutes is equal to 3,600 seconds. So if 1 hour is equal to 3,600 seconds, it means 24 hours will be equal to 24 times 3,600 seconds, and that is equal to 86,400 seconds. Now, to solve for the mass, we use two equations. The first equation is Q is equal to IC. This is the quantity of charge, current, and times time. This is related to the mass of aluminium obtained, but that's what we are supposed to calculate. We don't know it, so is equal to M. The current is 300,000 amps times the time is 86,400 seconds, and that is equal to M. This gives us 2.592 times 10 exponent 10 coulombs, and that is equal to M. This is equation 1. To do equation 2, we have to consider the half cell Al3 plus 3A minus, giving us Al. We know that 1 Faraday is equal to 96,500 coulombs, and 1 Faraday is the charge on 1 mole of electron. But in this equation, we have 3 moles of electrons, so it means you have to calculate the charge on 3 moles of electrons. So that would mean 3 Faradays, and 3 Faradays is equal to 3 times 96,500 coulombs, and this is equal to the mass of aluminium produced or obtained in this equation. So we don't know that yet, so I'm going to represent that with M. We also know that amount is equal to mass over molar mass, and so it means that the mass of aluminium produced in this equation is equal to amount times the molar mass, which is in this case the atomic mass of aluminium. The amount of aluminium in this equation is just 1 mole. 1 mole, that's what is obtained. And so it means that our amount here is 1 times the atomic mass of aluminium from the periodic table is 27. So 27 grams per mole. It means that the mass obtained is 27 grams. So it means that this M is 27 grams. So we have 289,500 coulombs is equal to 27 grams. This is equation 2. We can now use ratio and proportion on equation 1 and equation 2 to be able to find the M in this case. From here, we can just do cross multiplication to find M. So it means we have 289,500 coulombs times M is equal to 2.592 times 10 exponent 10 times 27 grams. So we divide through with 289,500 coulombs, 289,500 coulombs, and then our M is equal to 2.4 times 10 exponent 6 grams. D. Explain why chromium metal cannot be obtained by the electrolysis of dilute aqueous chromium 2 sulfate. Your answer should include data from the data booklet. We have to compare the chromium half cell to the standard hydrogen electrode, since the standard hydrogen electrode serves as a reference cell. Now, from the data booklets, the electrode potential value of the chromium half cell is negative 0.91 volt, and that of the standard hydrogen electrode is 0.00 volt, which means that the standard electrode, the hydrogen half cell is more positive than the chromium half cell, and so because of that, the hydrogen ions are going to be accepting electrons in order to undergo reduction, or in other words, reduction is going to be occurring at the hydrogen half cell and not the chromium half cell, which also means that chromium ions will not be reduced to form chromium metal. And so we have to conclude this by saying H plus ions are reduced instead of Cr2 plus ions. Thank you for watching. See you again in the next tutorial.